Okay, so recording the lesson on linear regression for our third unit in this class of fall 2020. So what is a regression line? It's a straight line. Well, lines are straight. That describes how a response variable y changes as an explanatory variable x changes, often used to predict the value of y for a given value of x. Okay, and we should know linear equations. Y equals mx plus b. Remember, m is your slope. And b is your y-intercept. Now, it's kind of weird over here. B is actually considered the slope, and A is considered the y-intercept. It's kind of strange. I'm not sure why it's done that way, to be honest with you, but it's okay. But, what we're going to really think about is how does x change with y, right? Now, it's called least squares regression line, or sometimes it's abbreviated as LSRL. Least squares, and you'll explain why it's called least squares. You'll see why it's called least squares in just a little bit. But the method is that you find the line to be as close as possible to the data points in the vertical direction, since that's what we're trying to predict. So like when you have a scatter plot, you have a bunch of like random dots, like that, right? And if you drew a line through those dots, that's what you're trying to do there. You're trying to find the line that's as close as possible to all those points. So least squares, what it does, you use the line that minimizes the sum of the squares of the vertical distances of the data points from the line. So for example, let's say I look at like this data point right here. And what I do is I take whatever y values on the line and whatever y values at that point, I subtract those two, and then I square it. And I do this for every single data point. And the hope is that I try to minimize all those squared differences. That's how we wind up getting the equation for this. Y squares, because when you square something, obviously the value is positive, right? So if we only sum the vertical distances themselves, the positive and negative values could cancel each other out, and then you might not quite be able to get the equation of the line. So that's why we square them, keep them positive. Now, sometimes it's written like this. So yet another way of another notation thing. We call this y hat, and that's going to be the predicted response or the predicted value. X is the explanatory variable, so it's whatever you plug it into your equation. And B is like the slope, and A is like the y-intercept. And just so you know, R is the correlation coefficient, which is not the same thing as slope. Correlation coefficient, remember, was a metric we used to see how well X and Y are correlated with each other, and it ranges from -1 to 1. That's what we talked about last week. And there's kind of a wacky form that goes with that, but you could just use Excel or Google spreadsheets or your calculator to compute that. And here's an example of a regression equation. Obviously that's your y-intercept, and that's your slope. And we see that the slope is negative. So what this tells me is that there's probably going to be a negative association between x and y. So as x gets bigger, y is going to get smaller, and vice versa. Now, before I get into how to calculate the slope of a regression equation or the y-intercept, it might be helpful to look at a tangible example. So I'm going to be tooting my own horn here. As you guys know, I love NFL football. And I think I shared with you guys a week ago that, this was like during week 6 of the NFL season. Kansas City was playing at Buffalo. And I think actually they weren't supposed to play on a Monday, but or actually they might play on a Tuesday, I can't remember. It's because of COVID situation with players testing positive. And I had built a model. You can see that this is a linear equation where 37.728 times f16. So I have a positive slope here. My y-intercept is -0.1376, which is kind of weird. But I use this equation to predict what the point difference will be for NFL football games. The way I did this back in the day, I looked at several years of data, Actually, I think like 2 or 3 years of data. And I looked at what were the point differences for different football games. And I also wound up doing some weird stuff where I found this one metric on a site called Football Outsiders that's used to rank teams. And I looked at the difference in that metric for 2 NFL teams. Like Kansas City is obviously very good. They won the Super Bowl last year. Their metric is 0.243, whatever. It's called DVOA. It's some weird formula that some website Football Outsiders came up with. And of course, Buffalo doesn't have a great number. And I found that, if I take the difference between this could lead to a pretty strong correlation with the actual point difference in the football game. And Kansas City actually won that game by 9 points. It was 26-17. Well, here's the cool thing. So there were games this past weekend, and Kansas City obviously played. They played the New York Jets. New York Jets are a terrible football team. And so their DVOA rating, the Jets, it's negative 0.439. The Chiefs ranking is one of the highest at 0.257. So my formula anticipated that the Chiefs would win the game by 26 points. The Vegas point spread was 20.5. It was actually the 9th highest point spread in NFL history. It's rare for a football team to win that by that many points, as well as just being fair by that much. And only one of those 8 other games did the favorite team actually win by more than the published point spread. Well, this is what happened on Sunday. Where do I have it? It's right here. The Chiefs won 35-29 by exactly 26 points. So my model actually was better than what the Vegas odds makers think was going to happen. Of course, they create a point spread to find the middle ground because they didn't know half the plug might bet over, half the plug might bet under that total. So that's an example of linear regression, and how some people can actually use it to their advantage. I got lucky, of course. But then the other thing is that I used it for Pittsburgh was playing at Baltimore and the Raiders were playing at Cleveland. And they were both underdogs, but my model actually, the Raiders were underdogs by 2.5 points. My model had them only losing by 0.16 points. My model had the Steelers only losing by about 2 points, even though Vegas had them lose by 4.5. In fact, Las Vegas and Pittsburgh outright won those games as underdogs. So again, my model was able to find me good value there. So again, it's all kind of cool stuff. I think it's fascinating. I mean, you can use it to predict any scenario. Data is data. It could be for any industry you want. But this is what we're kind of working our way towards, is building a linear regression model. And this is part of your project, and so that you'll do in spring. And so, and I want to kind of encourage you to kind of think of something and share in the discussion topic this week that will relate to this stuff. Now, how do you actually compute? How do you actually get the slope of the linear regression line? How do you get the y-intercept? Again, Excel will do it for you. The calculator can do it for you. But what is it actually doing? What the calculator is doing when it calculates the slope of the linear regression line, it takes a correlation coefficient and multiplies it by the ratio of the standard deviation for y. So in my case, it would be the standard deviation of the point differences. That was the response. Explanatory was I'm using this metric that I found on some website to explain why a team wins by a certain number of points, right? I want to understand that so you can make money when you're predicting football outcomes. And this is the standard deviation of X, of course. So that's how the slope is calculated. That's what the Excel or the calculator will do. The y-intercept is found by taking the mean of y, and that's the mean of x. And of course, my slope is b. So you got to calculate the slope first, then you do the y-intercept after that. Just the correlation coefficient and slope have some relationship, of course, but they're not necessarily the same. They would be the same if the standard deviation of y and x were identical, but that's not really going to be true for most of the time. And distinction between explanatory response variable matters. If reversed, you do get a different equation. The correlation would be the same, but like if you reverse these, whatever x, y, then of course the slope would change because now you're doing the standard deviation of x, over y that gets flipped, and this gets flipped also. And it's always going to pass through the mean of both x and y. So whatever the mean you have for x and y for your two sets of data, your line will pass through that point. X bar minus y bar. Again, x bar is the mean of x, y bar is the mean of y. So that's kind of the theory behind it. So what we'll do, we'll take a look at life expectancy for various countries in Europe, and per capita GDP. Per capita GDP is gross domestic product. That's basically a sign of like wealth or income. How that exactly is calculated, I'm not 100% sure. I got to dust off my economics textbooks. I don't have an economics textbook, but I'd have to look it up. But you can say like people in Switzerland. You might have heard like kind of the joke about Swiss bank accounts. If any of you guys have watched the movie Wolf of Wall Street, great movie, a little bit inappropriate, but he had a Swiss bank account, and there's a part in the movie where he was trying to fly to Switzerland and the plane crashes. But anyway, if you watch the movie, you know what I'm talking about. But there's a lot of money there, right? And people tend to live a long life. Ireland, you can see, has lowest GDP. So we're kind of curious, can we build a model for this, right? To get the slope, you have to do this. To get the y-intercept, you have to do this. But what I'll do instead, let me actually, hold on. Hold on a sec. I'm trying to get my pointer here so I can actually copy and paste the data. I don't know why it's not letting me. Hold on one sec. This is being stupid. Oh, there we go. Okay. I do not know why. It's probably because it's an image. Now I know why it's an image. So I'll have to type this by hand. Okay. I was trying to copy and drag it, but I can't. It's an image. So anyway, so here's what we'll do. So I did share with you guys a Google, we can close the football outcomes, and we can close the center and prayer. We can close this textbook. Actually, I'll leave it open, and we might need it later. But anyway, I share this spreadsheet with everybody, so everyone has access to this. So you should be able to have an example of how to build linear regression models, and you can use this for your homework, or during the breakout session, we'll start the worksheet. You can use that to help you. So anyway, let me actually set it off like this, and let me put this here. Okay, so I'll label this as GDP and life expectancy. And let's see, we got 21.4, 23.2, 20, 22.7. It's a little cumbersome, but it won't take long. 20.8, 18.6, 21.5, 22, 23.8, and 21.2. So it's 10 countries, that's correct. I probably should put the countries right next to them, but that's okay. The life expectancy was 77.48, 77.53, 77.32, 78.63, 77.17, 76.39, 78.51, 78.15, 78.99, and of course 77.37. Okay. So the first thing I'll probably wind up doing is let's get the mean for each of these. So let me actually insert this. Let me highlight this or bold it and center it as well. So let's center everything. It's always nice to center everything if you can. Let me expand that just a tad. Let's make that into a table. And we'll call this X, and we'll call this Y. Okay, so I want mean X, mean Y, standard deviation x, standard deviation y, and r, correlation coefficient. Okay, so in order to calculate, it's real easy to do equals average. And you simply just select those. And then do the same thing, equals average. You select all these as well. So again, this is recorded, so you have this for your reference. Equals and standard deviation. We're going to do the sample standard deviation. It's dot S of this. And then equals standard deviation, the sample one right here. And then equals correlation. And we want this, comma, this. That's a correlation coefficient. Okay. Now, to actually compute the slope and y-intercept, here's what we're going to do. Slope is r times sy over sx. Y-intercept is that. So to get my slope, then r times sy over sx, or 0.809 times sy, which is 0.795, over sx, 1.532, we'll say. So I'll probably just do that right here. Slope and y-intercept. Okay. And actually, I could just let Excel do the magic here. So I'll do E6 times parentheses E5 divided by E4. So that should be my slope of my regression equation. And then going back to my notes again, the intercept is going to be y bar minus b times x bar. So in this case, I'm going to do y bar, which is E3, so equals E3 minus E2 times my slope, which is E7. So my regression equation is this: y hat equals 68.715 plus 0.42 times x. So what this means is that if your GDP is 0, so if your country's broke, then you're gonna live to 68 years old. That's what that means, the y-intercept. Now what this means, the 0.42, is that for each increase of 1 for GDP, so as every time GDP goes up by 1, life expectancy goes up by 0.42 years. So, so if your country all of a sudden starts increasing GDP, you're going to live longer by 0.42 years, or that would be maybe about like 5 months. So if you're going to expect to live a certain amount of age, then they'll go up. A lot of times life insurance companies will sometimes look at this because they want to know how long you might potentially live and how much they should insure you for. Retirement planning, that matters too. They do look at GDP, other factors like what state you live in. Sometimes some, of course, your health and your diet, those are things that matter too, obviously. Medical history, if you have cancer in your family or other stuff, or heart disease. Those are all genetic hereditary things. But still, it's interesting, right? It's kind of cool. Now, what you could do is you could actually just let Excel do the magic for you instead of doing all this stuff it did off to the right here. I could just sort of just highlight these cells and hit insert. Insert a chart for me, please. It's a little slow, okay? So you can see I see a scatter plot. The scatter plot's not great because I kind of want to make it a little tighter for y. Right now it's going from 0 to 80 and the dots don't really seem too scattered so much. But you can change that if you like. So you could do is you could, obviously off to the right gives you an opportunity to kind of change your setup. So for my y-axis, let's go to customize. Now let's go to vertical axis, and let's go to minimum value. So minimum value is 60, and max value say is 80. So you can see it does it a little bit, a little more scattered, I suppose. If I just click on it, it kind of allows, pulls up, allows me to edit again. Now, the thing that I will want to do is let's actually do, hold on a sec here. Yeah, if you click on series and click on trend line, and I want the trend line to be linear, I want them to show me my R squared value. And I also want to see the equation that goes with it. So if I click on legend, no, not legend, sorry. Not chart style, not that. Maybe back to series again, because I do want to see the equation for that. And it should give you the equation. Use equation, there we go. Gives me the equation right there and my R squared value. So again, Excel can do all this for you. So can the graphing calculator, which I'll show you in just a little bit. But you see definitely 0.42 and definitely 68.7. So we got that calculated correctly. So I'm very happy about that. My R is 0.809. Well, if I square 0.09, so if I square E6, so parentheses E6 raised to the second power, you get 0.655. Now, why would we want to square R? I'm going to get to that in just a little bit. Like, how come R is not good enough? Why should I square the R? I'll explain that in just a little bit. Anyway, so this is just kind of good to know. So we'll go back to our notes again. All right, so now let's talk about R squared. So R squared measures usefulness of regression prediction. It tells us how good our prediction is. So what is R squared really doing here? It's a variation in y hat as x pulls it along the line. So basically, how good is y hat predicting our results? Divided by the total variation. So I know it seems kind of weird. So let me kind of go back to this again. So R squared is 0.655. What that means is that 65.5%. This is very important, by the way. And you're going to see this in the reading, and I will quiz you guys this on Thursday, because this is kind of the essence of what we're doing here. 65.5% of any change we see in life expectancy can be explained by changes in GDP. So any change you see in GDP, 65.5% of that change in GDP will explain, let me rephrase that. Whatever change you see in GDP, 65.5% of the change that happens in life expectancy is attributed to change in GDP. So for example, if life expectancy goes up from like 79 to 80, so your life expectancy went up by 1, of that 1 year, 0.655 of that 1 year was attributed to that change in GDP. That's what it means. So you could think the GDP actually seems to be pretty important. It has a pretty big impact on life expectancy according to this model. So that's what R squared is. It explains the change in variation of a variable based upon the explanatory variable. And that's kind of what's described over here. Rarely do you get R squared as 1. It's highly high. I mean, that's just like, yeah, everything's perfectly correlated, but it's rare that happens in real life. Usually R squared of like 0.5 is pretty good. If you have R 0.7, R squared is 0.49, like that's pretty good. Then we're going to talk about residuals really quickly. So a residual, what that is, that's going to be a plot where what you're doing is you're taking the observed value right here and the predicted value right here, and you're taking the difference between those two. And a residual plot looks like this. This is y minus y hat. And this is for various x values. Remember, x was GDP for us. So what you're going to do is you're going to kind of like plot y minus y hat for all your different data points. So what I could do is if I go back to my Excel spreadsheet, and the reading will explain all this as well. Let me insert. Okay, let me actually move that. So we'll do close residual. Let's bold it. Let's do this. And actually, let's do predicted also. We do need prediction. So this is the prediction based upon our model. So remember, our equation was 0.42 times GDP, which is, we'll say A3, plus our y-intercept, which of course was 68.72. So that was the prediction. I'll just do that. The residuals, you take the observed, so it equals B3 minus C3. And you do this. Oh. So now what I'm going to do is I could do a plot of GDP. Follow this right here. So if I hit insert chart, that's not what I wanted to see. So let me go edit chart. And I want that to be a scatter plot. There we go, perfect. Okay, let me move this down. Okay, let me clear my screen. So notice how some of the dots are above or below the x-axis, because some residuals are positive, some are negative. You want randomness. Randomness is a good thing. Like you want some. Sometimes you want your trend line to overpredict. Sometimes you want it to underpredict. If it's always above, then it means that the observer is always higher than the prediction. That means that you're underpredicting. If all the residuals are below, that means that y minus y hat's negative. So it means y hat's overpredicting. So you really want some randomness here. You don't want a pattern. So you want randomness for a residual plot. That's a good thing. That will tell you, and we're going to talk about this a lot throughout the whole year. So don't worry if you're not quite getting it yet, you will. But doing the reading will help you help reinforce this concept of residuals. So we're covering a lot of rich stuff right now. So this is good stuff. I'm very happy with the progress we're making here so far. So you guys are going to do a sort of worksheet in just a little bit. Let me finish up these notes here. So it's used to assess the fit of a regression line. And you look for a random scatter. If no, it could be problematic. Sometimes if it falls kind of like a quadratic model, or if it looks like a bow tie, sometimes that happens. There's some other issues that could be going on there. Those are not good things. That means that you need to go back and clean up your data. Maybe there's an outlier. Outliers, like, okay, that seems unusual. Like going back to my football prediction, when I did build this model, I did actually look at some outliers. Like, what if a team won by 50 points? That doesn't usually happen. So I'm going to remove that data point and look at everything else. I want to look at things that are more typical. So, or what if like a team that was not expected to win, wound up winning by a lot of points? Like that seems like an outlier. Like the Jets beat the Chiefs by 30 points, that would have been an outlier. I would have removed that. And try to look at more of what's the typical data. But of course, be honest with what you remove too. That's the other thing that in the second semester when you guys are doing your project, I'm also going to encourage you guys integrity of data, right? Because you lose your integrity when you hide data. And I also want to teach you guys how to be critical of data too. Like we hear all these things about what's going on in the news about the COVID cases and about getting a little somewhat political, like Trump claiming that he's had the biggest job growth during his administration. He did have the lowest unemployment rate for sure. Yeah, 3.5 before the pandemic. But I want to teach you guys how to be more critical of data and how to actually look at it and trust it. So that's something that we'll maybe explore in the second semester. Outliers, again, we've had that discussion before. Those are things that are just really just far off the reservation. They seem just really weird, and they can really influence your least regression line. So sometimes you want to remove that. Just an outlier and influential point are typically considered the same thing, but more specifically, we would say an outlier is influential if it's a huge outlier in X direction. It's really causing a major change in the slope. Then typically we want to get rid of that. And there are ways you can determine what would be an outlier or what would be an influential point. We're not going to do that today because I've given you guys a lot of stuff to think about. Correlation and regression, remember, it's only describing linear relationships. So not everything follows a linear model. I mean, there are other models we could do too, like exponential models, other stuff. This is when, if you're going to major in statistics or take more advanced statistics courses, you go down that road. My hope is that I leave you some stuff so that when you go on to college, if you do take more statistics courses, you can build upon the knowledge you have here. Of course, it can be affected by outliers, plot, so you can see what's going on. I wouldn't really necessarily extrapolate, like, oh, what happens if I extend the graph? Like, what if the GDP of a country is really high? Like, let's say some country has a crazy wealth. Like, let's say the GDP is like 40. Are you gonna live to 105 years old? I don't think so. There's only a limit how long you could live, right? So be careful about extrapolating or extending the data. But interpolating, like looking within, that's okay. Lurking variables we'll talk about maybe next time on Thursday. So they're the things that can have a relationship among, like, it's another thing that could explain what's going on. That's what lurking, like if you're lurking, like why else would still be someone living a long time? Maybe they have better doctors, maybe they haven't had like wars in their area. There could be other things that be explained besides money. And remember, association is not necessarily causation. Like just making more money doesn't mean you're going to live long. There are a lot of people who make a lot of money and die young. That happens, right? And a lot of very poor people. My grandfather was very poor and lived to 91, right? So, you can't really say that either. There is the causation, however, is there evidence that something might cause it? Sure, like if the association is strong, it's consistent. If you repeat things over and over again, like if you keep doing a study over and over again, kind of get the same results over and over again, you change the conditions, you still see the same thing happening. If you increase the explanatory variable, does that still increase the response variable? So all those things, that we'd have to look at. And those are things we'll talk about again later in the semester about designing experiments. There's some stuff you can do in the TI calculator, but you know what? I'm not going to do that today. Maybe I'll save that for Thursday. I want you guys to do some practice right now. I've shown you guys do in Excel. You guys have a copy. So what we'll do is this. I'll break you guys into 3 groups again. So we'll call it group 1, 2, and 3. So we'll go back to the Google spreadsheet. So let me close. I don't need that stuff anymore now. I don't need that open anymore now. Here we go. So let me create 3 more sheets, and we rename them. Group 1. Group 2. And group 3. Okay, I'm gonna make the groups random. Now, what you guys are gonna do is you guys are gonna start your homework basically. You're gonna get your homework out of the way. So I'm trying to reduce your homework load because I know tonight's a big deal, watching the election results. And but it's not just about presidents, it's also about all the propositions too that are a big deal. And of course the Senate races and stuff like that. And locally, whatever's going on in your neighborhood. So anyway, your homework, why did I close Schoology? Let's go back to Schoology one more time. So your homework is this. Statistics, here we go. Homework 14. So there's a worksheet here. It says no residuals. We're not gonna do anything residuals today. We're just gonna focus on just the regression aspect of things. Easier if I pull it up on my end over here, in my Dropbox folder. Unit 3. So there's only 2 problems you have to do. Here's problem number 1, and here's problem number 2. Everyone's gonna work on problem number 1 right now. So in your group, you're all gonna work on problem 1, and I'm gonna look at your work on the shared Google spreadsheet to make sure that you guys are doing it correctly. You guys can look at each other's work too, or working, I guess. You could lurk over someone else's shoulder, see what they're doing, just make sure you're doing it right. That's fine, that's what you learn. We have, I guess in this case, we're looking at pine cones and their offspring. So the cone index is X, and it looks like there's 4 rows here, but the first and third rows are gonna be your first column. So what you're gonna do, I'll kind of help out group 1 a little bit.
Mr. Almasi, is this, I can't seem to find the email where it was shared. Oh, I was searching something. Never mind.
You got it? Okay. No worries, you're good. So cone index, and what's the other one? Offspring. Okay. So you're gonna make 2 columns. So I really, actually, just to be fair, I'll do this for the other groups as well. So the first and third rows will go in the first column. The second and fourth rows will go in the second column. And I'll be watching, make sure you're typing the data correctly. So maybe assign one person to kind of type in the data. But you guys will be just working on problem number 1. And then you're gonna make a scatter plot just like I did. And tell me what the form, association, strength of relationship, like maybe you could type something, and you guys can all share. Like maybe someone does part A, someone does part B. Google spreadsheets are awesome. Everyone can chime in, right? So then calculate from the scatter plot, get your regression equation, or do what I just did. You totally could just copy and paste what I just did in sheet 1. Let me call this classroom demo. Yeah, you totally could do what I just did, right? You can copy and paste the stuff here if you want. I could just delete that because I don't need that shown. And then you're going to interpret what the slope means, plot the regression, use regression, and I'll kind of go through these with you guys. And use regression line to predict the number of offspring when the index is 3.5. So anyway, I'll put you guys in breakout rooms. We'll do it for 15 minutes. We'll come back around 1:36. We use the last 3 forms to discuss what you guys did, and then we're done for today. So let me stop sharing. Let me stop the